So I'd like to introduce, it's a shame in Brazil, we won't make the football, but I would like to introduce Jo Nelson from Rice University. She'll be speaking about cylindrical contact homology.
Right. Thanks for the invitation. IMPA has been really great. I think it's the most beautifully located math institute I've been in yet. So, all right. So I first kind of want to give a little bit of history about where contact homology came from, and kind of go in the more contact direction than Marta went. Because in the symplectic world, you had the Arnold conjecture that kind of motivated the development of everything. And in contact homology, we had something called the Weinstein conjecture, which has motivated a lot of the subject. And then for kind of, I don't know, historical overview-y type purposes, there's two articles on the archive. So one is by me, and it's very light. It's mostly anecdotes. There's little math, but this is from dynamics to contact and symplectic topology and back. And then the other one is by Michael Hutchings, and this one has a lot of math in it, but it's an overview of Taubes's proof of the Weinstein conjecture. In dimension 3, and so if there's not really a nice survey article about contact homology, I would say, but these kind of two articles will give you some history and some context and hopefully help give some more background. So last week there was this really nice summer school about celestial mechanics, and we learned from Urs that the moon is what gave us symplectic geometry, because understanding the periodic orbits of the moon is quite difficult, whereas the planets go along pretty much in elliptic motion. And anytime you have these systems where you have a conservation of energy and you're trying to understand motion and looking at periodic orbits, this gives rise to symplectic geometry. And then if you want to restrict to a hypersurface in your symplectic manifold, then you're naturally going to come up with a contact type condition. And then it turns out to also be interesting to study sort of contact manifolds in their own right. And that's kind of how the subject started to develop. So in the 70s, the sort of main players in contact geometry were, of course, Arnold, and then you had Rabinowitz and Alan Weinstein. And what they were doing is they were proving the existence of periodic orbits of the Hamiltonian vector field restricted to a hypersurface, typically inside of R2n. And they were trying to figure out what sort of hypersurfaces could you restrict your Hamiltonian vector field to and still get periodic orbits on them. And Weinstein proved that this is true on convex compact hypersurface. And I mean, now we think about a convex compact hypersurface inside of R2n, and we think, oh, that's the canonical example of a contact manifold. It's very natural that it should admit periodic orbits coming from the Rabe vector field, but at the time that got you an Annals paper. And actually, I talked to Alan a little bit about some of the history, and he told me that initially the authors of the Annals didn't think that anyone cared about convex compact hypersurfaces, but Paul Rabinowitz and Rabinowitz's advisor Moser had written letters to him, and so Alan mimeographed these letters and sent them back to the editors of the Annals to show that people did indeed care. So I mean, that's maybe not what you want to do now today, but I guess it's kind of good to see that everyone kind of struggles a little bit to show that their work is interesting and relevant. And then Rabinowitz had a series of papers, so this was 77, 78, and 79, and he extended this result to star-shaped hypersurfaces. And star-shaped means that if you take a ray coming out of the origin, it intersects the boundary transversely. So you don't want sort of like weird shapes like this. So this is not star-shaped. Okay. And Rabinowitz used an action functional that at the time his advisor said would like never work. And actually his advisor had bet him a quarter that he couldn't get the proof to work. And when I gave colloquium at Wisconsin, where Paul was for many, many years, some of the analysts there told me that Paul still had this quarter from Moser that he had kept for proving this result. So I guess maybe now like the price of these results has gone up a bit, but. Okay, and then, so Alan Weinstein kind of was a big pioneer of symplectic and contact geometry, and in this written correspondence between Moser and Rabinowitz, and sort of his methods for convex compact hypersurfaces, and then seeing that Rabinowitz got it to the star-shaped hypersurfaces, Alan realized that this star-shaped condition is exactly a contact type condition. So in order to get a hypersurface inside of R2n to be a contact manifold, which is sort of compatible with the contact form comes from the symplectic form on R2n, that the star-shaped notion is precisely the condition you need to get that hypersurface to be contact. So Weinstein in '79 wrote a short paper where he makes the Weinstein conjecture. And this is where he came up with the notion of a contact hypersurface. And so the original form of his conjecture looked very different. There were some conditions on the homology of the hypersurface, because that was kind of a thing that you did back then, and it was just about hypersurfaces sitting inside of symplectic manifolds. But sort of now the modern formulation of the Weinstein conjecture is that if you have a closed oriented contact manifold, then for any global contact form which defines the contact structure Xi, the associated ray vector field admits a closed periodic orbit. And this is kind of remarkable that this conjecture has stuck around and was exactly kind of this contact condition was exactly the correct condition to impose, because in sort of the late 80s, early 90s, there was a lot of energy around the Cipher conjecture, and the Cipher conjecture said that on any closed sphere, there should exist a closed periodic, if you have any closed, or a sphere is closed. Okay, you have a three-sphere, you have a smooth vector field on it, then there should exist a closed periodic orbit. But the Kuperbergs came up with counterexamples and to this, and so it was really remarkable somehow that the Brabe vector field condition will exactly force your vector field to have a periodic orbit, whereas if we relax this to just be a three-sphere in any smooth vector field, you can show that there are vector fields which do not admit closed periodic orbits. And the Weinstein conjecture kind of motivated a lot of machinery to try to understand contact manifolds and to better understand Rabe dynamics. And this is really well encapsulated in a quote by someone at their 60th birthday conference, and he recalled that when he was a graduate student, he said, "Why did I come into symplectic geometry? I had the flu, and the only thing to read was a copy of Rabinowitz's paper where he proves the existence of periodic orbits and star-shaped energy surfaces. So I guess in the 70s they didn't really have Netflix. So it turned out to contain a fundamental new idea, which was to study a different action functional for loops in this phase space rather than for Lagrangians in the configuration space. And that's exactly what Moser thought would never work. Moser has a paper where he says that this action functional is certainly not suitable for an existence proof. And then Paul proved him wrong like a year later. All right. And actually, if we look back, this approach of using the action functional for loops in the phase space led to the variational approach in symplectic and contact topology, which is the action functional that Marta wrote down earlier this morning, for example, which is reincarnated in infinite dimensions in Floer theory and has appeared in every other subsequent approach. The flu turned out to be really good. So the flu turned out to be really good because that individual was Hofer. So Hofer, with various people, so there was Conley, there was Zander, there was Viterbo, and then there was Strua. But these guys were kind of all proving various, trying to push the results of Rabinowitz and Weinstein a little bit further, so looking at hypersurfaces inside of cotangent bundles, looking at hypersurfaces in more general symplectic manifolds, and they pushed the Weinstein and sort of Rabinowitz variational methods, which are semi-infinite dimensional. And so this was all through sort of the late 80s. And then the main breakthrough was Gromov's theory of pseudo-holomorphic curves. But Gromov didn't really, he used it to prove the non-squeezing theorem and another of other really beautiful results. But Gromov was not he didn't grow up in this world of variational principles and hunting for periodic orbits, so he didn't really see the value in his pseudo-holomorphic curves, and in that direction, and Floer came along and saw that. And actually there's a quote by Gromov about how he has never forgiven Floer for morsifying his pseudo-holomorphic curves when Gromov was awarded the Steele Prize for his research, and he said that, alas, history does not pay the loser. So somehow, I don't know, you have to be a little bit brave in this field, I think. But then what Hofer did is he sort of adapted Floer's ideas in closed symplectic manifolds to study J-holomorphic curves in symplectizations of a contact manifold. This is the symplectization, and by doing this, what he was able to do is he looked at J-holomorphic curves, and there wasn't a perturbation by the Hamiltonian vector field, but you have a similar asymptotic condition. And what he was able to do was he showed that finite energy implied sort of existence of a holomorphic plane, which limited on a closed Rabe orbit. Which would then imply the Weinstein conjecture for S3. Okay, and this was, I think, it was published in Inventiones in 1993. And pseudo-holomorphic curves and symplectizations are kind of, the natural notion of energy isn't quite right because it ends up being infinite, but Hofer came up with what is now called Hofer energy, where it just kind of it takes the supremum over like a band of energy in some sort of window in the R component of the symplectization, and then that finiteness tells you something about holomorphic planes, and sort of the bulk of this paper is trying to understand how these moduli spaces work, and that there's kind of some weird compactification phenomenon showing up, which implies that you sort of can break off these holomorphic planes which have limits on closed Rabe orbits, and this sort of failure of compactness actually led to a proof of the Weinstein conjecture. And then sort of in the meantime, people were really pushing ideas of Floer theory really far, and Lagrangian Floer theory came up, then symplectic homology came up, and Yasheli Ashberg was really interested in sort of contact manifolds in their own right, not just as hypersurfaces of symplectic manifolds, and so this led to the creation of what people thought would be symplectic field theory, which would like rule all of symplectic geometry, but it was maybe a little bit too ambitious. And kind of in the meantime, Hofer, along with Chris Vysotsky and Eddie Zander, they really developed the theory of pseudo-holomorphic curves and symplectizations, and they used it to prove a number of deep dynamical results. They came up with global surfaces of section. They proved sort of more quantitative results. So they were able to show that S3 as a contact manifold, if you have a convexity condition, it has to admit 2 or infinitely many closed Rabe orbits. And so you can really push a lot of these pseudo-holomorphic curve ideas quite far to understand dynamical information. But kind of people in the meantime wanted to try to push pseudo-holomorphic curves to get some sort of a contact homology theory. And then because there were all these different Floer homology type theories, the idea was that you would have symplectic field theory, so this was sort of proposed in 2000 by Eli Ashberg, Giventhal, and Hofer. And this was supposed to capture somehow all possible Floer theories. For contact, symplectic, and then you have Lagrangian and Legendrian, and you have Gromov-Witten and marked points and everything. Okay, but this was sort of very far-reaching, and there are a lot of analytic difficulties that show up, which I'll touch on a little bit in the next 2 lectures. But they kind of impede this symplectic field theory from being realized, and that's why sort of polyfolds have been developed and why there's all this interest in sort of Kuranishi structures. But that goes really far beyond what I want to talk about today. So I'm going to kind of keep myself to one of the facets of this theory, which is called cylindrical contact homology. And so, I don't know what. So symplectic field theory somehow is just very broad, very far-reaching. It really contains sort of all the structure you could possibly hope to have in all these Floer homology theories. It was 100 pages, but it had no proofs. And if you read like the Math SciNet reviews of the paper, it says like, this paper is so beautiful, this like concept is so wonderful, it must be true, we can't wait to spend the next 5-10 years proving these ideas, and 20 years have now passed and we're only beginning to sort of scratch the surface. Okay, so now I guess I will start actually saying a few things. So for the rest of this hour, I want to tell you about the chain complex. So it's going to be a little bit different than in Hamiltonian Floer theory. So we're somehow going to kind of forget the action functional because Hofer came up with how to understand moduli spaces of J-holomorphic curves, and so we're just going to take what Hofer did with J-holomorphic curves with Chris Vysotsky and Eddie Zander and sort of see how to define a differential. So this is going to be generated by good closed Rabe orbits. So I'll define good in just a sec. We have to kind of take a step back and talk about the Conley-Danger index. And this will be as a vector space over Q. And the differential is going to count index difference 1, J holomorphic cylinders interpolating between closed Rabe orbits. And in the contact world, the sort of index we're going to be using is the Conley-Danger index, which is a Maslov type index. And it's a sort of winding number that you can associate it to an arc of symplectic matrices. And we'll see how to extract an arc of symplectic matrices, basically when we restrict the flow of the Rabe vector field to the contact distribution. Okay. So then the goals for today are going to be sort of a definition, why d squared equals 0 in an ideal world, and some hints, or not hints, but I guess a glimpse of sort of compactness and transversality problems, or I guess interesting phenomenon for multiply covered curves. And Marta, of course, couldn't sort of go into all the compactness and transversality sort of things that go into Hamiltonian Floor theory, but towards the end of her second lecture, she had written down some sort of conditions about the first Chern class and symplectic area and stuff, and somehow J holomorphic curves and closed symplectic manifolds, you can control the energy a lot with these area conditions that just depend on the first Chern class, and so you hear words like semi-positive and monotone, and that's sort of like enough to control compactness issues so that you can get that d squared is 0 and you can show invariance. But in the J holomorphic curve world and symplectizations, there's not such an easy analog that you can use, and sort of another issue is that in Hamiltonian Floor theory, you are using just your chain complex is just generated by time 1 closed Hamiltonian orbits, whereas our chain complex is going to be generated by closed Rabe orbits, and sort of each embedded orbit and all of its iterates are generators. And so the fact that you include the iterates of the Rabe orbits as generators is what's going to lead to you having multiply covered curves, and sort of the transversality for somewhere injective curves breaks down once you have multiply covered curves, and it creates a lot of difficulties. But this is somehow like the right complex to consider in a way, because it kind of mimics the homology of the free loop space. And so you want to sort of see each circle as well as all of its iterates to try to extract kind of the maximal amount of information. Okay. Oh, and I guess the last thing I should say about the Weinstein conjecture is that in 2006 or 2007, Cliff Taubes proved it in dimension 3, and he used Seiberg-Witten theory to prove it, which is another pseudo-holomorphic curve theory, which goes far outside the scope of this summer school. But what's related to Seiberg-Witten theory is embedded contact homology, and Vinicius is going to talk about that. And the embedded in front of embedded contact homology is what's going to make it much nicer in some sense, although you're not going to be counting cylinders, and so it's going to look a little bit more scary, but the embeddedness of it means that you avoid these transversality difficulties for multiply covered curves, which is great. But it's kind of hard when you first see this subject and you're like, oh my god, how many contact and symplectic and Hamiltonian homologies can these people come up with? And the answer is that it's never ending. Okay, so m to n minus 1, kernel lambda equals c is going to be our closed oriented contact manifold. And we're going to also assume that lambda is non-degenerate. In order to say what non-degeneracy is, you have to talk about the Rabe vector field and look at the flow. But you basically want to think of this non-degeneracy condition, if you haven't seen it before, as kind of like a Morse condition. And so this will force all of the embedded Rabe orbits to be isolated. So this is kind of like a Morse condition. And the Rabe vector field, this is defined by the equations lambda of r equals 1. And the contraction of r with d lambda is 0. And so non-degenerate implies that the embedded Rabe orbits are isolated. And gamma, a closed Rabe orbit, is embedded whenever the map from R mod TZ, where T is the period or the action of the Rabe orbit, into your contact manifold M is injective. Okay. And then, because we have d lambda and c, that's going to give us a symplectic vector space. Because the contact condition means that d lambda restricted to its kernel is non-degenerate, which just means that C is a symplectic vector bundle when paired with d lambda. And so that's going to give us a J, an almost complex, it's going to be a complex structure, and we can extend that complex structure to 1 on the symplectization. So this is a symplectic vector bundle. So it's in 1-to-1 correspondence with complex vector bundles. And there exists a bare set of complex structures compatible with d lambda on C. So that means that we get a Riemannian metric which is positive definite. And such a J, there should be a J, is said to be lambda compatible. Okay, and then we can extend this J to 1 on R cross M because the Rabe vector field gives us a splitting of the tangent space of our contact manifold into the rave direction plus the contact distribution, because the flow of the rave vector field needs to be transverse to the hyperplanes, and so you can split into the rave direction and the contact distribution. And right now we have a complex structure on the contact distribution, and we're going to extend it to one on R cross M, basically by intertwining the rave direction with the extra R action on the symplectization. Extend J to an R invariant almost complex structure. So here tau is the coordinate on R by J dd tau equals R, and then we want J restricted to the contact distribution to be one of these d lambda compatible almost complex structures. And such a J is going to be said to be lambda compatible because there's this canonical way to extend it to the symplectization where you're just intertwining the R direction of the symplectization with the rave direction. Okay, and now I need to say a few words about what's going on with sort of the rave orbits and the linearized return map. So also kind of what's going on is because this is a symplectic vector bundle, locally along a closed rave orbit, we can trivialize this symplectic vector bundle, which means that we can identify it with just R2n minus 2 with the standard sort of complex or symplectic structure. And then we can use that to take the derivative of the flow of the rave vector field, which will restrict to the contact distribution. So locally, we trivialize C d lambda j along a closed rave orbit. And then we can consider the linearized return map, which we write as d phi t. So here phi sub t is the flow of R, the rave vector field, and we're going to restrict it to the rave orbit gamma. This is going to be a map from it's going to be a map from one symplectic vector space back to itself, because this orbit is going to have period t, so after time t it comes back to itself. And once you have sort of, if you look at any time t in 0 to big T, this is going to give us a path arc of symplectic matrices. But the linearized return map is sort of the most, like it really encodes a lot of information because it tells us that after big time t, how much do we kind of change this symplectic vector space? And because this is a map of symplectic vector spaces, at time t we're just going to have a symplectic matrix, and we can look at the eigenvalues of that symplectic matrix. So contact form is going to be non-degenerate whenever all of the eigenvalues of the linearized return map restricted to the contact distribution are not equal to 1. So that means that they're going to need to come in pairs of complex conjugates, or they're going to come in pairs of real numbers, or you have the real number and 1 divided by the real number, because you know the determinant of a symplectic matrix needs to be 1. And the eigenvalues of this linearized return map are sometimes called flow K multipliers, and they're a really kind of important thing because they tell you sort of how much the flow along an orbit kind of distorts a vector space. And so that's kind of the first dynamical handle you can have on something. Okay. So the eigenvalues of d lambda t come in pairs. So either they're complex conjugates, or they look like lambda and 1 over lambda, where lambda is real. Okay. And then in dimension 3, this is going to be a 2-dimensional symplectic vector space. And so the linearized return map is just going to be a 2x2 symplectic matrix. And so there's sort of 3 possibilities really for what the eigenvalues are. So they're either complex conjugates, they're positive real numbers, or they're negative real numbers. Okay. And this is going to be important for Vinny. And in the case that you have complex conjugates, then your array orbit gamma is going to be said to be elliptic. If you have positive real numbers, then gamma is positive hyperbolic. And if you have negative real numbers, you're going to have that gamma is negative hyperbolic. Oh, well, I had written that I'm assuming that lambda is non-degenerate. Otherwise, you could have 1 as your eigenvalues. Okay. And, right. So in higher dimensions, you can still kind of have elliptic and hyperbolic, but it stops to make, like, it doesn't make as much sense to consider that because you don't have as nice of a control on your Conley-Zander index formulas, and things break down a bit, and it just turns out that in dimension 3, it's really nice to know this like elliptic, positive hyperbolic, negative hyperbolic dichotomy. And it also shows up when we want to talk about good ray orbits. And then because I wanted to actually write down some formulas for the Conley-Zander index for you to show that you can actually kind of compute it, you need to be in dimension 3 because otherwise in higher dimensions you can't just kind of write down the Conley-Zander index formula as cleanly. Here. So if gamma is embedded in elliptic, then each phi t is rotation by angle 2 pi theta t with big theta equal to theta t, and this is for some sort of nice trivialization. So this Conley-Zander index formula will sort of hold regardless of the trivialization you pick, but there is a nice trivialization for which you can realize each of the symplectic matrices in this path is rotation through some angle. And so with respect to this trivialization, you'll get a nice formula for the iterates of the Conley-Zander index in terms of this rotation angle, and this is going to be 2 floor k theta plus 1. For different trivializations, you'll still end up with some sort of theta, but it's just not going to be realized as some sort of rotation angle. But this is kind of nice because it shows you that the Conley-Zander index is really kind of encoding some sort of winding information that's very geometric in nature. And then if gamma is hyperbolic, then the flow rotates through angle pi r with respect to a suitable trivialization. As you go from time 0 to time big T, and then you'll have that CZ with respect to this trivialization of gamma k is going to be equal to kr. And here, what's kind of remarkable is that this r is actually an integer. And it's a well, it can be 0. And r is going to be even if gamma is positive hyperbolic, meaning it has positive real eigenvalues, and it's going to be odd if gamma is negative hyperbolic. Okay. Elliptic, hyperbolic. And I'm going to put embedded in here because otherwise it gets a little bit confusing to start to think about iterates and Conley-Zander index formulas. It's easiest to just write the iterates in terms of the underlying embedded Rabe orbit, but you can do it. You can remove this sort of embedded from each of these things if you want. Okay, and then a fun fact about the Conley-Zander index in sort of any dimension. So in any dimension for either the Conley-Zander index on the iterates of, when you look at the iterates of the Rabe orbit and you look at the Conley-Zander index, it turns out that the parity of the iterates either stays the same or it changes. So either the Conley-Zander index of gamma to the 2k plus 2 mod 2 is equal to the Conley-Zander index of gamma to the 2k plus 1 mod 2, or the parity changes. And here, gamma is embedded. And in the latter case, the even iterates of gamma are said to be bad. And they're called bad Rabe orbits. And then if a orbit is not bad, it is good. So I didn't come up with these words, but not bad. It is good. Okay. But this is like some kind of irritating vestigial thing where you'll find in any field, people will like get to some technicality and they'll be like irritated by it and they'll be like, it's bad. And then they'll make some ridiculous arbitrary definition and they'll be like, that's bad. And when it's not this, it's good. And you're like, this is not helpful to anyone. But anyways, so what's nice when you work in dimension 3, you have these formulas, and it turns out that sort of the way that, like, you may change this theta, you may change this r, but if gamma is positive hyperbolic, it turns out that r is always even and r is always odd if gamma is negative hyperbolic. So in dimension 3, the bad the bad Rabe orbits are always going to be the even iterates of negative hyperbolic orbits. of embedded negative hyperbolic orbits. Okay. And there are some sort of technicalities we're not going to get into about good and bad. But basically what happens is that when we look at moduli spaces where you interpolate between a Rabe orbit where one of them is bad, it turns out that you can't sort of orient that moduli space. And then there's also there's something called a period doubling bifurcation, and the context structure is unchanged before and after, but the Rabe dynamics are changed. And you can show that sort of locally, if you were to include bad Rabe orbits, that before and after the period doubling bifurcation, you get different answers for the homology of your chain complex, which is not ideal. And so to avoid that situation, you have to throw out the bad Rabe orbits. So there's not really like a good satisfying reason why we have to throw them out at the moment, but you can just take my word that you do. And when Vinny gives his talks, you'll see that in the embedded contact homology chain complex, elliptic orbits are treated differently from hyperbolic orbits, and it's for a similar sort of reason, although not sort of identical. But you'll unfortunately continue to see this junk about elliptic and hyperbolic orbits, and it's important in dimension 3.
Is there ever a case where embeddedness is sort of like failed, but this still structure is working out?
No, this is still true even if gamma is not embedded.
But you're saying there are some nice features that come along with the case.
Well, I'm just trying to make it less confusing in terms of like classifying all the bad Rabe orbits. Because you could kind of more generally say that regardless of this embeddedness, you could ignore this, and then you have this, and then you could say that the even iterates are all going to be bad, but those even iterates are always going to come from an even iterate of an even iterate of an even iterate of a embedded negative hyperbolic Rabe orbit.
I think you say that every Rabe orbit is a cover embedded Rabe orbit.
Yeah. Great. Okay, so then in 10 minutes, I will say what the differential is, but we now can say what the chain complex is. And for Eliashberg, Giventhal, and Hofer, I'll have a little EGH there. So this is going to be generated as a vector space over Q by the good Rabe orbits. So for the differential, we're going to keep this J, and then we're going to extend it to an R invariant, almost complex structure on the symplectization. And a lot of times you include generic, which just means you kind of picked one. Well, okay, it doesn't mean that you picked one of these elements out of the bare set at random, but for now we can pretend that's what it means. So JV generic, almost complex structure, which is R invariant on R cross M and lambda compatible. Sometimes lambda compatible also means that it's R invariant on the symplectization, but I just want to emphasize that you're extending the J from your symplectic vector bundle to the symplectization in this nice way. Okay. Then the moduli space of J holomorphic curves interpolating between two arbitrary Rabe orbits, so we're not going to assume that they're embedded. They can just be any Rabe orbits you want. These are going to be maps from a cylinder. To the symplectization. And you want the J holomorphic curve equation to be satisfied. Then you want an asymptotic condition to be satisfied that involves the Rabe orbits. And then I'm going to have T as my domain component corresponding to S1, and S is going to be my domain component corresponding to R. So if I look at the limit as S goes to plus or minus infinity of the projection to R of my curve U, I want this to be plus or minus infinity. And if I look at the limit as S goes to plus or minus infinity when I project this curve to the contact manifold, I want this to be a parametrization of gamma plus or gamma minus. So if it's plus infinity, I want gamma plus. If it's minus infinity, I want gamma minus. And then I'm going to mod out by automorphisms of the domain. Okay, what do I want to say here? Okay, so the kind of picture is if I pretend that my contact manifold is a circle, and then this is the R component, then my pseudo-holomorphic curve has a limit at plus infinity on gamma plus and at minus infinity on gamma minus. And then it can do whatever it wants as long as it satisfies the J-holomorphic curve equation. Okay, so this is why you always see these pictures of cylinders, and then you can also have curves with an arbitrary number of negative punctures and positive punctures and genus. And so you'll see like all these weird pictures inside of soda cans, and those are just J-holomorphic curves and symplectizations or cobordisms. Okay, then the index. So given U in MJ, gamma plus gamma minus, you can define something called the Fredholm Index. And this is going to be the Conley-Zander index of gamma plus minus the Conley-Zander index of gamma minus. And so when I talk about the differential counting index difference 1 curves, that means that it's going to go between, I want to look at pseudo-holomorphic curves that interpolate between a Rabe orbit, which has Conley-Zander index greater than the Conley-Zander index of the Rabe orbit at the bottom. And then there's a beautiful story about spectral flow that we can't get into, but basically the d-bar equation, it looks like, or you put the bar there, this is dsu plus j dtu. This is like another way of writing this. If you linearize this, you get an elliptic PDE. And then there's a Fredholm theory, which is associated to elliptic PDEs. It turns out that the index is given by the dimension of the kernel minus the co-kernel. And what's really remarkable is that with Riemann-Roch and spectral flow, the index is actually governed in terms of the difference between the Conley-Zander indices of the asymptotics. And so that kind of tells us that somehow the Rabe orbits are really kind of guiding the analysis and why we want to start to maybe make a chain complex to understand something about Rabe dynamics and to hopefully come up with a contact invariant. Okay, let's see, right. Then this is maps of cylinders into a symplectization. We've modded out by the automorphism group of the domain. I think tomorrow we'll see a talk where we're looking at closed holomorphic curves. So there'll be maps from just Riemann surfaces into a closed symplectic manifold, and then the automorphism of the group involves like PSL2. Anyways, but you always end up modding out by sort of automorphism groups of the domain when you talk about moduli spaces of J holomorphic curves. But then also we have this R action on the target. So just like in Morse theory and in Hamiltonian Floer theory, because there's this additional R action, we want to mod out by that R action as well. So MJ, gamma plus, gamma minus, is just going to be this moduli space modded out by the R action, so of the target. And then the way that the index changes, well, maybe I don't want to write it quite like this. Okay, usually the Fredholm Index is supposed to not care what automorphism group you've modded out by, but the virtual dimension of mj is going to be the virtual dimension of m twiddle j minus the dimension of the space of automorphisms of R, which is 1. And this virtual dimension of mj is given by the index of u. So it's just going to be Conley-Zander index of gamma plus minus Conley-Zander index of gamma minus 1. And so the idea is that if we could make kind of all the ideas from Morse theory and Hamiltonian Floer theory carry through, if I looked at index difference 1 curves, after I mod out by R, I would be looking at a 0-dimensional manifold, because this index difference would be 1, and then I minus 1, so that's 0. And if life is good, and my linearized d-bar operator is surjective, then I would know that this moduli space is cut out transversely, which would mean that it's a manifold. So if I have a 0-dimensional manifold that's compact, it would have to consist of a finite number of points. And so that would tell me that the differential would just consist of counting this finite number of points. So it would be well defined. And the way that you would want to prove d squared is 0 is when you look at d squared, that would count index difference 2 cylinders, or sort of broken cylinders. The virtual dimension of that moduli space is going to be 2 minus 1, which is 1. If you can compactify that moduli space by sort of including some broken curves, then a compact 1 manifold has to have an even number of boundary points. If you count them with sign, they would cancel. And so that's how you would get that d squared is 0. So that's kind of what you want to end up saying to get that the differential is well defined and that d squared is 0. There are going to be some kind of transversality and compactness difficulties that I'll get into the next lecture. So let me very quickly write down the differentials, and then we can take a break. Okay, so there's 2 ways to define the differential. So one way, which I'll write as delta kappa, so x is going to be the Rabe orbit at the top, y is going to be the Rabe orbit at the bottom. This is going to be the count, assigned count over the curves that go between x and y, and then I want y to be index difference 1 from x. And then I'm going to have to encode the multiplicity of x and the multiplicity of the curve u. So this is going to be u in m1, in mj xy, and this is going to be y, so that the Conley-Zander index of x minus Conley-Zander index of y equals 1. And this delta and kappa, they're going to be encoding this like multiplicity business. The other way is going to be kappa delta, and so here I'm first going to encode the multiplicity of this, or I'm going to end up encoding the multiplicity of the bottom Rabe orbit. It's the same stuff that you sum over, except now you encode the multiplicity of the bottom orbit rather than the top. So here, delta is a chain map. It goes from C star EGH to C star minus 1, and it's just going to encode, this is going to be the sum over all the y's that are index difference 1, and the u's that, well, it should be u, not y. And then you have a signed count, which you need to adjust by the multiplicities of the cylinders by. So it's a weighted signed count. And then kappa is going to be a map just from C star to C star, and it's going to be pretty boring. It's just going to encode the multiplicity of the orbit. Okay, and so to say something about the multiplicity of the orbit, so m of gamma embedded is equal to 1. M of an embedded Rabe orbit, if you take its k-fold iterate, which I'll write as upper script k, this is going to be equal to k. And I'll sketch why d squared is 0, and when I do that, we'll kind of see why we have to do this weighted count. And because you're kind of multiplying, dividing by multiplicities, and you see like greatest common denominators and least common multiples show up when you do gluing. That's why there's these two different ways to define the differential. The reason, in part, why we work over Q is because we're multiplying and dividing by multiplicities. And while these coefficients are integers, if you want to show that the homology with respect to this differential is isomorphic to the homology with respect to this differential, the chain map that you would need to write down would need to multiply and divide out by multiplicities, and in order to do that, your chain complex would have to be over Q. So sort of the little picture to see what's going on is that if x is gamma plus to the k p, y is gamma minus to the k q, this would be a k to 1-fold cover of a cylinder that goes between gamma plus to the p and gamma minus to the q if the GCD of p and q is equal to 1, and I'm assuming that gamma plus and gamma minus are embedded. So here, the multiplicity of u would be equal to k, because it's a k-fold cover of a somewhere injective cylinder, because the greatest common divisor of p and q is 1. Then the multiplicity of x would be kp, and the multiplicity of y would be equal to kq. And so if you want, like if your multiplicities of x and y, like in order to have a cylinder which has some positive multiplicity, it needs to have iterated orbits at the top and the bottom so that it can cover another cylinder. And so that's always going to force this term here and this term here to be integers. So the differential is like a little bit weird, but we'll see when we look at why d squared is 0, why we kind of have these weighted counts show up. And the fact that we have to include these weighted counts kind of suggests that there might be some transversality difficulties. You don't see these weighted counts in Hamiltonian Floer theory because you're just looking at time 1 periodic orbits. You're not looking at orbits which are multiply covered. So I'll stop here.